C++ tutorial, lesson 129, take 32, me first. Hello there, this is Al, and this here is lesson number 129, hopefully entitled Me First. Me first. The question or the statement or the want of pretty much every programmer refers to the fact that everybody at some point wants to get the first crack at something. That is, it would be great if there were some way in your program to be able to say, this is definitely going to happen before that, right? This happens before that, and nothing can happen before that thing, whatever, that line of code. It turns out, though, that is pretty much impossible. You can't say that about any line of your code unless you're talking about a specific program. This, well, I'm in the wrong project, but any one of these programs, let's take this here. Okay, so taking this touch here, yeah, I've been through this. I ran through this and the recorder wasn't running, so let me go through it again. I'm going to make a statement very quickly, and then I'm going to change to the remainder of this video, which has already been recorded. Here is a simple program that does something. Okay, it sets the time and date of supply. What my statement is that there are a few things that we can be 100% certain about in terms of the order in which some things happen within your program. And one of them is the following: simple data type, simple data object declared at global scope will have been set before the program begins execution. Okay? That's my statement. Therefore, it follows that this statement could not possibly execute before this statement, even though it appears ahead of it in the file. Okay, this is one type of assignment. This is another type of assignment. Both are, variable equals data. However, this assignment requires the execution of some code. The copy constructor. This doesn't require any code execution. In fact, this assignment occurs and is done by the operating system during the process of loading the program into memory. And that's easy enough to understand, because what I did here, just taking an example, is I did a dump bin of some program into clipboard, pasted it into Notepad, and pointed out at least one of the sections of data, not for that program, but those simple data declarations and assignments and whatnot at global scope are all placed into the binary executable file. Now these are actual memory addresses, okay, and after the program has been fully loaded into memory, before it has started running, these addresses in memory will have been filled in with this data, just like this. This assignment is done in here. So this assignment is done before the execution of any code, and so therefore I know that this line is executed before this line. It turns out that in terms of the order in which these variables, although it doesn't really matter because you can't do anything about it, the order in which these variables are filled in is in the same order as they appear in any one particular source file. However, if you have many modules, you can't be sure how they're mapped into memory. If you wanted to be sure, and many people do this, especially people who write C programs, is they only compiled exactly one source file. They set every single source file to not compile, and then they have one CPP file or C file, and they include everything one after another after another. That way they can ensure the order of assignments of all the various variables. If one thing refers to another, they can know for sure that by forcing the ordering that it'll work. Okay, so I'm going to stop this and continue on with what I already have to prove what I just said. I made a statement, and I should be able to back it up. Oh, and I need a simple example. I need a simple data type and a simple object, both declared in global scope. Okay. How about a rectangle? Now this is a constructor. 1, 2, 3, 4. How about this? Well, let's see, I'm not sure now. Now it gets complicated. I think I need to do anything. Oh, it's complaining because I haven't given a different name. Get rid of all this. Turn everything off. And build it. Now, here's a question. Oh, excited. Now, the question is, well, firstly, this has a default constructor which sets everything, which makes everything invalid, makes the rectangle invalid by making the right equal to -1 and left 1, so it's inverted basically. The left hand side is bigger than the right hand side, and the bottom the top is, right? This is not invalid. No, bottom has to be bigger than top, but here it's less, right? Well, I'm not using the default constructor. I'm using this constructor. The question is this going are these variables going to be 1, 2, 3, 4? Because that's the way they're listed in the argument list. Or is it going to be the invalid rank? And actually, I don't know the answer. Now we can print it out. We can just step to here and see what it is. Watch. Okay, so that worked. So this construction occurred before this happened. But see, now these weren't declared as simple data types. They were declared as equal to function call, right? Now, I want to prove that if I didn't do that, that these, suppose I set these to something recognizable. I want to prove that I'm sure it's true that these values these values will be set before this constructor gets called. Now, how am I going to prove that? Let me think for a minute. Okay, one way to prove it is to not use that structure, but make up a new structure. Let's struct. I think this one takes long. Yeah, it uses long. It's just like the Windows rec. Oops, 4, not F4. And we'll just pass that on to the parent and the superclass. Okay, now at least now I want to declare it too. So that's fine as it is. Now it's our own class and we can do something possibly. Now, this declaration is certainly before this, but it's my assertion that this function call will happen afterwards. And how do we check it? How do we check it? It's tricky. I don't want to call a function here, right? I want to put down I1 plus anyway. I could have just said I2, Y1 plus 1. How can we look below? Let me think about this for a minute. Okay. Here I've declared my A structure. Okay. Here's its constructor. And in that constructor, which should be called from this line, this could be on a separate line if you want. You like it that way. Okay. Now I want to prove that this line is executed before this line. Alright? Now in the constructor here I'm asserting, now this is just viewing I as an external array. So that's not a function call, it's just a memory lookup, and we can disassemble it and double check and make sure that that's true. Okay? And it's looping through and ensuring that these have already been set up by the time the constructor is called. If the assertion goes off, I'm right. If the assertion doesn't go off, if the assertion goes off, I'm saying that they're equal. If the assertion doesn't fire, then I'm right. If it does fire, then I'm wrong. Right? Wrong or right? Right. That would mean that they've been set up already. Well, I didn't hear any assertions go on. Here are the I's. What are the R1s? Okay, it's got its 1, 2, 3, 4. Right? But this assertion didn't go off. Now, it could be that without the reference to the I's, maybe the order would have been different. And that's difficult to, maybe not so difficult to prove, but let's just step up to here. Okay, if you look at the call stack, this is coming from C init, right? C init is a function. It's called after CRT startup, which is the entry point of our program. We haven't hit main yet. Even the other main that's supposed to happen before this main, I think we haven't gone to that main. That we're in this main. There's no main at all in here, right? Everything's main CRT something. And now we're on the call init turn. So none of the code in common or in utest or whatever has been executed, other than if it has, it's been done through this init turn. Okay, not by any deliberate calls. Now it's clear. IS is not this. The int star is set up with its numbers, right? And what does the code here do? Where are we? We're supposed to be here. Alt 7. No, that's not the right line, definitely. It may not be able to show us exactly where it is, because also the debugger isn't. Oh, well, here's the line. Okay. Now, all this part does is make everything invalid. Move into AX, D word, let's get rid of some of these things here. Show source code. I want to see this part. I don't want to see symbols, at least not yet. I want to see the actual code and how it's going to do this comparison. What's that call to? That's a call to the constructor. Okay. So that's a call to the parent constructor. Here, this is the jump. So that now that occurs before we go into our loop. I'm trying to figure out where the loop is. I put it all on one line, unfortunately. It's 37 hex. Okay, so that's the adding something to 55. EBP minus 8. Now, negative things that we subtract from are local variables. So that's being created on the stack for us. You add to the stack point. Sorry, you subtract from the stack pointer to allocate. 10. Okay. This is taking, what was passed in and doing something. I'm just trying to find out where the loop begins. Here's the comparison. So this is part of the loop. Where's the loop part? Here's like the crash with the assertion failed. Move into this, move into that, if equal. Oh, compare, thank God. Okay, this is a comparison. EAX, which has been set where? Well, it's been going like crazy. Different things. And somewhere here, EBP, okay, now that must reference I, the loop variable. Yeah, okay. Now I would initially have been set to 0, right? And it's being compared with 4, that's when we put the loop. And the comparison is EAX times 4 plus DX. Now EAX is I, and this here is simply an address, right? That's how you can think of an array of integers. It's an address, square, then followed by some square brackets, and an offset, a byte offset in assembler. And so now this address 4C9898. There. Okay, 55, 56, 57, 58. Now you can be certain, and I'm telling you right now, that we're going to find that sequence, as long as this allows me to dump this well. It doesn't matter if I stop the program. It wouldn't have let me run this until I stopped the program. Maybe it would have, just for reading. Anyway, just remember it was 37 onward. So 37,000, then 38,000, and on. 4 of them, and they should be in the executable image. They're not loaded dynamically, or this is not a dynamic load. It happened before everything. Why is it taking so long? Everything's slow. Something's slowing everything down. Anyway, I'm going to pause this. Yeah, well, it is running slow, but anyway. Now, that's writable data, so it won't be in the read-only section. It'll be somewhere in here. And we'll look for space 37 space. And we'll find it eventually. And if I just missed it, that's certainly not it. Well, it could be. No, they have to be lined out as an array. That's the way it was declared. 38. Did I just miss it? I'm going to pick the best. Oh, the last one, I think. I know what to look for. Start with data. Now they may not line up exactly in one row, but I keep trying. Eventually I'll get one of them. So at some point it's got to say 37 followed by that many things, and then 38, and there should be a space on either side here. 39, 38. So here it is. Alright? Now that everything that's in this dump out, printout, is what gets loaded into memory by the operating system, by Windows NT, before the program is allowed to begin execution. Right? Now my assertion was that therefore it follows that, assuming that the mechanism for implementing a declaration like this is to put it into the binary, and we've just seen, maybe it may have been a coincidence, but we could try another sequence and see if it's still true. We'll do that. We'll use X. How about E, B, 11. I don't know. No, 11. No, why not? How about 71? BE. Okay. Now the assertion is going to go on because it's not 55 anymore. So what I need to do is just say it by hand. I need 4 loop. I don't need a 4 loop. BF 71 EE. And that's whoops. All it's doing is it's in its constructor, which happens after the program gets loaded. So all it's doing is it's taking a known offset. The linker, when the linker's done its job, we'll fill that part in, and these will be set up after the construction. These will be filled in before this thing gets constructed. And first, we check to see that no assertions go off. Okay, it's the same address. Now we look into the binary again. I hope that it just. I guess I'll find out. I restored the encoder there by accident, which is why I like to put it there. And it looked like it was in a funny state, so it's possible the last 5 minutes or 10 minutes weren't recorded. But I'm telling you now, we're going to find this sequence in the exe. Let's paste it. AFBF 71. Oh, see, this much. There, okay. And the next one should be 71, then EE. Okay? Now that's not a coincidence. The chance of both of those things happening, none of those assertions going off by random coincidence is 0. And so therefore, the order of declaration is not necessarily the order of construction, if you like. This, in a way, is a type of construction of an array. but it's not constructed. It's simply set. It's by the time the program is running, right? Like what, when you get out of bed, this has already been prepared for us, right? Now our program is allowed to do stuff, right? And that happens before main. This part also happens before main, and this part happens before this. So this simple data assignment part is the first step in the construction of all the objects in your program. The second step is the construction of globally declared objects, and that's done through this init term. If you recall, we step up to here, call stack. Okay, here's init term in the runtime library. Okay, now if def cout. Okay, we're not DLL, so that's why we're in here. It's a static function called init term, and it takes two pointers, a beginning and an end pointer of something, of PVFB. Now that sounds to me like pointer to something function something, possibly. And we'll call this dynamic initializer for R1. Dynamic initializer for R1 is being called by init term, right? So init term is calling our constructor for us. Okay. Alright. Now before init term is cnit. Excuse me, this is code. Oh, this is cnit, sorry. It's called cnit. It's the name of this function. It declares an integer, not DLL. So this is what the code that gets executed. Now, there's a pointer involved here. That was what was passed in. No, this must refer to a globe. Oh, a globe. Oh, this looks like a global. Well, it's not declared here or anywhere else, unless it's a macro referring to this, which I doubt. This is a global variable that it expects either, it expects this to both not be null and that this function in reference to it is true, and that says is non-writable in current image. Then it calls, it's a pointer to a function. Okay. Oh, I see. If a particular pointer to function has been defined, and now they've got another function which will check to ensure that whatever this pointer is, it's in the non-writable, it's in the read-only data section, like where the virtual function tables are. I have a similar code like this in common for some things. To check to see if an object's virtual function table is valid, I check to see that it's in the read-only data section, and the way I do that is I try to write to it, and if an exception gets thrown, then I know that it's, well, at least more likely to be correct than not. Oh, and I also try to read from it. I have to be able to read from it, but not be able to write from it. If reading from it fails, then it's invalid. If writing to it fails, then it may be valid, but you can't say with 100% certainty. Okay. So now, if this did fail, that would indicate a serious problem that has already occurred. Like this has been replaced. It's passing the address where this thing is stored, though. Never mind, that's not our business. Now we're on init term. Now what's the difference here? Else if CRT DLL FP math. Oh, I see that it doesn't even have to do with it. Now how come init term E, there must be two. Okay, so there are two init terms, and the init term passes in two values. That first value looks like where our program begins. No, it's not. What is it actually? I lost that. 41A to 4A1 to 40 A to Z. Now I wonder how it must have, obviously these have been filled in already, but how? Right, this does seem like a sideline, but I'm curious. I normally am. Okay, then it calls that init term, and it takes those. If you can look at the declaration here, it says void star star. Okay, so pointer to a p void and another pointer to p void. Now pointers to p voids are things like virtual function tables. You have to take a star of that to get a kind of pointer, and what the thing points to is unknown. It's not specified there. Not specified in that function call. I'm just curious what these addresses correspond to. 4A1. Actually, there's not much, is there? There's only 240 hex worth of, well, from beginning to end. So divide by 4, right? 4A1, and then 240. And decimal. That pointer is 4 bytes. That's 144 pointers. $576 times 4. Yeah. What? Oh, so 144. 24. Okay, so there's no remainder. Okay. Now the four zeros is 4A we're looking for. No. 4A 1000. Oops. Hit undo. I forget how many times I hit undo. Press page down. The notepad's great unless if it's too, if the buffers, if you put too much into it, then it really slows it down with the editing. Not reading. Reading's okay. It doesn't expect to deal with large files. This kind of editor won't try to recalculate every single one. Oh, that's read only. Okay. And starting at 4A1000, so that's the read-only data segment. That's the beginning of the segment, all the way up to 240. It looks like it's all zeros. It's not. If these are all pointers to pointers, there are a few things set, and the rest zero. Now I assume that init term goes through. No, it can't be. Oh, if not, no. Okay. So it does check, and it's going through adding 4 bytes each time to see if there's a function that needs to be called, and then it just goes ahead and calls it. And the functions are of type void, returning void. Pointer to void function returning void. Okay, not so hard to understand when we see it. And that's what it takes this function to be. Now, there's nothing void about this function at all. This function has 4 arguments, so how could it be here? And the way it can be here is someone, the compiler, has come in and created a void function to, well, here, push offset pf in it. Well, I'm going to get rid of all that stuff. But push BP, moving to BP as a push, blah, blah, blah. This is called dynamic initializer for R1 bracket, bracket. No arguments, right? However, there's a callback here. Thread local storage, it's different. Init rep. Floating, it's like we're back into, I'm in the wrong line, that's fine, I'm on the wrong line again. I want to be on this line. It's, yeah, comparing the IS thing. So that's correct. However, as far as init term is concerned, everything is just void function taking no arguments and returning nothing. And the way that they accomplish that is obviously how do they do that? It's probably just hardwired in with the actual number setting. for the constructor. These are all the assertions. Where's the 1, 2, 3, 4? 3, 4, 3, 2. Where's 1? It's not 0, 2, 3, 4. It's int 3. Push 2, push 0. What happens? It's gotta happen first. Here. Might be easier without symbols. Now these have been passed in. Well, how did they get passed in? A function was called. I'm not sure what that is. Oh, here they are. There you go. 4, 3, 2, 1. It's just hardwired here. And so this function doesn't take any arguments itself. It pushes these arguments on the stack, calls the real non-void constructor, and that's just how that works. Okay, now I've wasted a whole bunch of time. I don't know what to do with this video. I've wasted too much time. I didn't get to my point. This will just be a sideline. Okay. Alright. See ya.